Evaluate two-sided limits analytically for rational functions with removable discontinuities by factoring. Alright, so let's just see how removable discontinuities and limits are connected and how they relate to each other. Alright, so quick review. The very simplest definition for removable discontinuity is a removable discontinuity is a hole in a graph. Now, there are two different subcategories for removable discontinuities, and these two graphs show the examples of both. We have one where the point is just moved up or down on the graph, and we have the other one where the point is completely removed entirely. So, if we were to look at limits of these graphs at the point of discontinuity, again, we know we have to look from the left and the right, but regardless, if we look from the left and we look from the right, we can see that even though the actual point is raised above the graph, that the limit still exists. There is an intended height for this particular function. So, regardless that if there's a removable discontinuity, the limit still exists. And the same is true for the second type of removable discontinuity, is that regardless of whether there's a point anywhere on the graph at x equals 2, there will still be an intended height, which means the limit does exist. So, moral of the story is, it doesn't matter which type of removable discontinuity it is. It doesn't matter whether or not the function is defined at that particular point. The limit exists no matter what. So, the limit will always exist at a removable discontinuity. We just need to figure out a process to find that intended height. So let's do that by looking at an example. So here we have the limit, as x approaches negative 3, of x squared plus 3x all over 3x plus 9. Well, I can go ahead and I can apply my properties of limits, and I can pull this apart into individual variables. But that takes a long time and is a long process, and I would hate to go through that entire process just to get an undefined term. So the only other method we have right now is direct substitution. So let's go ahead and let's apply direct substitution, and let's just see where that takes us. So that means I'm going to replace all of the x's with negative 3. So we'll end up with negative 3 squared plus plus 3 times negative 3 all over 3 times negative 3 plus 9. And if we continue simplifying, let's see, we're going to get 9 minus 9 over negative 9 plus 9, which gives us 0 over 0. Oh, so you might be thinking to yourself, wow, that didn't work, because 0 over 0, we've already learned that that is an indeterminate form, and that means we're stuck. And if you're thinking that, you're not wrong, because that's what 0 over 0 means. It means that it's an indeterminate form. But it doesn't mean that we're stuck, because this 0 over 0 actually tells us something very important. If you remember back to pre-calculus when you discussed removable discontinuities, you knew, or hopefully you learned, that 0 over 0 means that there is something you can factor out and cancel. So that's what we're going to do here. This 0 over 0 is a hint. It's like, hey, here's what you should do next. So whenever we see 0 over 0, we should automatically be thinking factor and cancel, factor and cancel, factor and cancel. So let's go ahead and let's come back to our original limits. So we're going to relook at the limit as x approaches negative 3 of x squared plus 3x over 3x plus 9. But instead of doing direct substitution now, we're going to see if we can factor the numerator, factor the denominator, and hope they have a factor we can cancel out. Well, let's see. If we want to factor the GCF out of the numerator, that would be x, leaving us with x plus 3. We can then factor GCF out of the denominator, which is 3, leaving us with x plus 3. And wouldn't you know it, we have a common factor. So since we have a common factor in the numerator and a common factor in the denominator, those can cancel out, leaving us with a simplified function of the limit as x approaches -3 of x over 3. So we factored and canceled, which means if we do direct substitution now, we shouldn't get 0 over 0 anymore. So that's what we'll do. Now we'll apply the direct substitution again to give us -3 over 3, which gives us an intended height of -1. So, quick recap. We did direct substitution from the get-go. We got 0 over 0. However, that was the clue to what we should do next, because 0 over 0 means we should factor and cancel. Went back to the original function, factored it, canceled, did direct substitution again, and got our intended height of -1. So whenever we're dealing with removable discontinuities, or whenever we get 0 over 0, that should be setting off alarm bells that says, factor, cancel, factor, cancel. So let's see it again. Next up, we're going to take a look at the limit as x approaches -1 of x plus 1 over x squared minus 2x minus 3. So, just like the previous example, we're going to try direct substitution and see what happens. If we get a number, huzzah, we're good, time to move on. If we get 0 over 0, that means factor and cancel. So let's do it, direct substitution, woo! Plug in -1 wherever we have an x. So we're going to get -1 plus 1 all over -1 squared minus 2 times -1 minus 3. Then we can simplify. So the top's going to be 0. The denominator is going to be 1 plus 2 minus 3, which gives us 0 over 0. So no, we didn't get a number, but yes, we got a clue. So we need to factor and cancel. So we're going to come back to our original limit, the limit as x approaches -1 of x plus 1 all over x squared minus 2x minus 3. Now, in the numerator, x plus 1, there is nothing we can cancel out, so we'll just leave that as x plus 1. However, the denominator is a quadratic expression, which we might be able to factor, and yes, we can. We can factor this into x minus 3 times x plus 1. And now we have a common factor in the numerator and a common factor in the denominator, so we can cancel those out, leaving us with our simplified expression of 1 over x minus 3. And then from here we will try direct substitution again, hoping to get a value this time. We'll get 1 over -1 minus 3, which will give us our intended height of -1/4. So there we have it, 0 over 0, factor and cancel, boom, got it, -1/4. And let's take a look at one more, because this one, it's not difficult, but it does kind of throw a monkey wrench into what we're doing, and I want to show you how to fix that monkey, or fix the wrench, or maybe nothing's broken with a monkey wrench. I always assumed a monkey wrench was used by a monkey. Maybe it's a wrench shaped like a monkey. Anyways, different discussion, different day. Moving on, we have the limit as x approaches 1 of x squared minus 1 over 1 minus x. So, direct substitution. So we're going to throw in the 1. So we'll get 1 squared minus 1 over 1 minus 1, which will be 1 minus 1 over 1 minus 1. And for some reason, sorry about that, my ink all of a sudden magically switched to black. But anyways, 1 minus 1 over 1 minus 1 will give us 0 over 0. And that shouldn't scare us, because that means we just need to factor and cancel. Alright, so going back to our original limit, we are going to have the limit as x approaches 1 of x squared minus 1 over 1 minus x. Alright, so we can factor the numerator. That's going to be, let's see, x plus 1 times x minus 1 all over 1 minus x. Oh, shoot. We factored, but there's no factors to cancel. Or is there? And this is a cool little trick. So if we notice, x minus 1 is so close to 1 minus x. If only we could just flip them both around to be x minus 1. But unfortunately, subtraction is not commutative, which means we can't just randomly flip them. So here's the trick. So let's take this 1 minus x factor. And the trick is, we're going to factor out a negative 1. It's going to be like, what? We're going to factor out a negative 1? How does that work? Well, we factor out a negative 1, that's going to leave us with negative 1 plus x. And now we have addition. And we know that addition is commutative, which means I can rewrite this as x minus 1. And wouldn't you know it, we were able to flip the terms by factoring out that negative. So now we can replace that in our limit to get the limit as x approaches 1 of x plus 1 times x minus 1 over negative 1 times x minus 1. And now, using that secret trick, we have a common factor in the numerator and a common factor in the denominator that can cancel out. Simplifying our limit to be the limit as x approaches 1 of x plus 1 over negative 1. We can now use direct substitution to get 1 plus 1 over negative 1, giving us 2 over negative 1, or an intended height of negative 2. So again, that trick right there of factoring out a negative 1 to flip the terms is going to come in handy every now and then. So it's one of those tools you just need to keep in the back of your head. All right, folks, and that is it for evaluating limits with removable discontinuity.